Assalamu alaikum and welcome to lecture number 28. In this lecture we are going to consider properties of the Fourier. So before starting the properties of the Fourier, let's do one more numerical problem on finding inverse Fourier transform. That is to find the inverse Fourier transform of the discrete time signal, right? So the signal we are given here is basically a pulse in frequency domain. So we have a pulse in frequency domain. Here it is defined that it is equal to 1 for absolute omega is less than or equal to W and 0 otherwise. So this is where it is defined. So let's find the Fourier inverse of this. To find the Fourier inverse, we use the synthesis equation. So this is the equation for the inverse. So the signal is 1, you can see, from minus W up to W, and we just say okay, e power j omega n and d of omega. Right, so you understand integration of this will be e power j omega n, and because we are differentiating with respect to omega, so the we'll scale it by 1 over j omega n. So we have something like j omega n divided by, that's 1 by 2 pi here, and we divide it by g n, right? And the limit of integration are minus w up to w. So by putting value we get 1 over 2 pi, let me bring n here, so that's 1 over 2 pi, and so by putting limits of integration we get so it's like a sine formula. So that means if I just bring j, we already have j here, so if I multiply, if I bring this to this side, so this one is sine, so that means we have 1 over pi n into sine of omega n, right? So this is a sinc function, you understand, and it has maximum value when n equals to 0, because if at n equals to 0, you can see if you replace n by 0, this is your x of n, so at that you get 0 upon 0 form, so you use L'Hopital rule and hope you can find this. So that's all for the numerical inverse Fourier transform. Let's start the new topic, Fourier properties. So the first property we are going to consider is the linearity. You understand what is linearity, right? You have learn it at maybe multiple occasions previously, right? So for example, we have z of t equals to ax of t plus b y of t, right? So the Fourier transform of it will be z of j omega, definitely, right? So it is equal to a times x of j omega plus b y times j of omega, right? So that also means that you find the z of t and then you find its Fourier transform, or you can also say that you say okay, z of t has Fourier transform of z of omega, and because x of t has Fourier transform of x of j omega, because Fourier is a linear operator, so we can say that if I scale it by a, the resulting Fourier transform is also scaled by a factor of a. Similarly, the superposition is here plus, so byt, so by y of t has Fourier transform of y of j. So if I scale it by a factor of b, so the Fourier will also be scaled, and when I sum them, the result will also be summed, right? This is for the Fourier transform. Again, we have the similar case or similar analysis for the Fourier series, so and a discrete time Fourier transform, and similarly discrete time Fourier series. You understand Fourier transform is used for aperiodic signal, whereas for periodic signal we use the Fourier series. So Fourier series, if the signals are continuous, then we use the continuous time Fourier series, and if the signals are discrete, then we use the discrete time Fourier series. So let's have a numerical example on it. Okay, so here is the first example, which involves the super linearity, right? So we have z of t equals to 3 by 2 times x of t plus 1 by 2 times y of t. Now one way to find the Fourier series of z of t is straight away we find the resulting signal, that is this here in the figure we are given the input signal, the two signals which are to be added, right? So 3 by 2 times of x of t plus 1 by 2 times of y of t, we add them and we get the resulting signal, which is z of t. And after getting the resultant signal, we apply Fourier series to find the Fourier series coefficients of z of t, right? The other way is that we go to the we find the Fourier series, we exploit the linearity property and we find the Fourier series of x of t and then y of t, and then we scale them by factor of 3 by 2 and 1 by 2 respectively, then add them and we get the resulting the required uh, coefficients. So if we add the two signals, it's very straightforward. You see that x of t has amplitude of 1 from 0 to 1 by from minus 1 by 8 to 0 to 1 by 8, right? And y of t has value of 1 for this range. So we just piecewise addition, you understand. So for the values minus 1 by 8 up to 8, because x of t is 1 1 and y of t is value of also has value of 1, but because we need to scale it by 3 by 2 and 1 by 2 for this one, so that's why we get 2, okay, here. So this is from minus 1 by 8 up to 1 by 8, whereas for the value 1 by 4, right, this is basically 1 by 4, so 1 by 4 up to 1 by 8, because the y of t is half, so it has amplitude of this. So I hope you understand, and once we find this one, we can straight away use the Fourier series analysis equation to find, because you understand, to find the Fourier series coefficients, because it's a periodic signal, so we have Fourier series, and in case of Fourier series you find the it on by integrating on any period. So let's take the original signal and find the Fourier transform individually, and then we scale them and add them. So that's how we exploit the linearity property. So let's solve it. So because we have already done the square wave example, so just using the value for t1, we can find that x of t has Fourier transform of Fourier series. So this Fourier series coefficients for x of t, 1 by k pi sine k pi by 4, and similarly for y of t, bk, and which is equal to 1 over k sine of k pi by 2. If you don't understand this, you can straight away again find the Fourier series coefficients for the individual signal, right? So scaling this by a factor of 3 by 2, in fact, right? 3 by 2, right? Because Fourier is a linear operation, so x of t scaled by this will also be, it's like 3 by 2. Similarly for y of t, we have scaling factor of 1 by 2. So if I scale it by a factor of 1 by 2, so it will be something like this, right? And z of t has Fourier transform, which is equal Fourier series, which is equal to summation of these two, right? So if I sum these, I get 3 by 2. So here we get the required signal, right? So again, I will say, if you cannot, so you can just recall the example of the square wave, and we have used it t naught and minus t naught, I think. So they can be replaced by 1 by 4 in this case, and in this case the t naught or t1, whatever we use, is 1 by 2 here, right? 1 by 4 here and 1 by 8 here. But if you cannot recall, you can straight away take the signal and take its Fourier series coefficients. I hope you understand how you can do it, right? You know the equation, which is 1 over t integration over t any one period, and x of t, right, multiplied by e power minus j k omega naught t dt, and similarly for y of t, right? So you can find the respective coefficients. So the other property we are going to explore today is the time shifting, right? So what happens when you shift the signal in time? For example, we have original signal x of t, and it is shifted by amount of t naught, and we represent the shifted version by z of t, so that z of t is basically time shifted version of the x of t, and it is shifted by amount of t naught. So let's see what happens in the frequency domain when we shift a signal by some value t naught in time domain, right? So let's take the Fourier transform of this. So Fourier transform is basically integration from minus infinity up to infinity. Hope you understand all these equations. Now, because we have the input is z of t is basically equal to x of t minus t naught, so replacing its value here, and we do the change of variable, and we say, okay, tau equals to t minus t naught, right? So when tau equals to t naught, t minus t naught, replacing t minus t naught here with tau, so it will result into this, and tau will be equal t will be equal to you understand, because if t naught comes this side, it will be plus, so we can say that t equals to tau plus t naught, right? So we replace the value of t here by tau plus t naught, right? So that's exactly what we get here. Hope that's quite straightforward. If I open, then I get x of tau e power j omega minus j omega tau, and then e power, right? You understand, because this is plus tau, so minus j omega t naught you get, right? So minus j omega t naught is constant because we are integrating with respect to the tau, so that means I can bring e power. You understand how I get this one, right? Because this is added, so we can write it like, so I can write it e power, if I open the bracket, I will have e power minus j omega tau minus j omega t naught. So if I can also write it like this, if I write here, so that means this one contains tau, and we are integrating with respect to tau, so it is in here, whereas this one is e power minus j omega t naught, so it's out here because it doesn't contain something like tau, so I bring it outside. Now this is basically Fourier of the x of t. So this is Fourier transform x of t. So that means if we shift a signal in time domain by a factor of t naught, in frequency domain it is just multiplication by e power j omega t naught, right? So this is for Fourier transform. We have done this one. Similarly for Fourier series we again have, but in Fourier series, instead of omega we have k omega naught, so it will be e power minus j k omega naught t naught, okay, and times the ak, because ak are the coefficients of the Fourier series. Similarly for the discrete time Fourier transform we will have this expression, and for discrete time Fourier series we have this. So hope this gives you idea. So let's consider a numerical example here. For example, x of t is as shown here, this one, and when we shift it by a factor of capital T, right? So it will be shifting to the right. So now we have the z of t, which is 1 from 0 up to 2 capital T, and 0 elsewhere, that is from 0 up to negative infinity, or from 2t up to positive infinity, it is 0. So let's exploit the time shifting property and uh, find the z of j omega, right? So we know for this case we have already done this, right? We already considered two examples for the pulse, once in continuous time Fourier transform and once in discrete time Fourier transform. So for the continuous time we get this thing, right? So that's our Fourier transform, right, for the x of t or the pulse, right? Now what we do is we replace omega by no, not replacing omega by this, but because we say in time domain shifting by uh, t naught, which is this one we have done. So in time domain we shift by this one, so we get in frequency domain it is e power minus j omega t naught multiplication. So it's equal to in frequency domain and time domain shifting by t naught corresponds to multiplication by e power j omega naught t. So in this case, because we are shifting it by capital T, so it will be multiplied by e power j omega and capital T, and the rest remains the same. So this is how we can exploit the uh, time shifting property to find the time shifted Fourier transform of the time shifted version for the signal. Okay, you can also do it by just shifting it, and then you take the Fourier transform of this. You will also get the same answer, but because in symmetry it's very easy, and we have done this for the pulse case in both in continuous and discrete time, so I think that's easy. Let's consider one more another property, that is time scaling. So you understand time scaling is scaling the signal, right, by the so I think this we have done in the first chapter, and we said and we proved there. We understand that if the scaling factor a is greater than 1, in that case the resulting signal will be a compressed version of the original signal, and if this is less, if this is between 0 and 1, then the uh, resulting signal will be scaled, a stretched version of the input signal, and how much stretching will be, it depends on the exact value of a, right? So let's we say that we have x of t z of t equals to x of at. That means z of t is the time scale version of x of t, right? So let's see what happens when we scale something in time domain. What happens, what effects are there in the frequency domain. So straight away we can write the Fourier transform equation, z of t power j omega naught t. Now z of t is basically equal to x of at, so e power minus j omega t dt, right? Now again we take the change the variable, right, the independent variable. So let we say tau equals to 80, so that means t equals to, so t equals to tau by L. So let's put it here. So we originally have x of 80, so instead of x of 80 we have x of tau now, okay, and then we have e power minus j omega, and because here we had t, so t is replaced with tau by a, so we just write minus j omega by a tau. Again for d tau we replace, so if I differentiate this with respect to time, so I get something like this, right, dt upon d tau, right, this is a t, so differentiating both sides with respect to time tau, so it will be dt by d tau equals to 1 over deta by deta, so that cancels, you get 1, and this is dt by deta, so deta goes this side, it will be multiplied, so you have 1 over a times deta, so that means dt is equal to 1 over a times deta, so deta here, and because a is independent of tau, so I write it here, right? So you understand, we have in term for the time scaling, we have two scenarios, that the scaling factor is greater than 0. Greater than 0 means there will be no reflection involved, and if we have smaller, a is smaller than 0, means it will be negative, so that means you are scaling as well as reflecting the signal. So if a is negative, then we are also doing the reflecting the signal. So in that case, we have 1 by a, and we have integration from infinity up to minus infinity. So we have two expression, right, depending whether the a is greater than 0 or a is less than 0. So we can, these two integrals may be combined into a single integral, and we can say that's basically z of j omega equals to, because 1 by a, so we can say, okay, 1 by absolute of a, and integration of from minus infinity up to infinity x of tau e power uh, j minus j omega by a tau deta. So that's a unified expression. So because this is the Fourier transform for x of omega by a, so we write 1 over a absolute x of j omega by a. So that's the resulting expression, right? So you can observe easily that when you scale the time scale the input signal in frequency domain, not only it scales the frequency, but it also scales the amplitude by a factor of absolute of 1 by a absolute, right? So let's have a numerical example on this. So for example, we have a signal x of t equals to this, right? And we have the its scale version uh, y of t, right? And y of t equals to 1 for t absolute is equal to or greater than t absolute less than or equal to 2, right? So that means we are scaling it by a factor of how much? 1 by 2. We are scaling here. That means y of t is basically equal to uh, x of 1 over 2t, right? So that's why the resulting signal y of t is straight version of the input signal, but is positive, right? It's 1 by 2 is between 0 and 1, so that means the resulting signal is straight by a factor of 2, but it is also positive, so that means there is no reflection involved. Okay, so we can do it either way. We can straight away find, because we know this, so we can plot the Fourier, we can plot y of t, and y of t is, because this is equal to 1 from minus 2 up to 2, so we straight away use the Fourier transform equation, analysis equation, and find the Fourier transform. Or we can also use this one, because we know that the Fourier transform of x of t, right? This is again a pulse, so we know that Fourier transform of x of t is, right? So it is like, we can say this is Fourier transform of x of t, and this is equal to this, right? So because y of t, we actually need to find the Fourier transform of y of t, right? So we need to find the Fourier transform of y of t, and we know that y of t is basically time scale version of x of t, so that means we can say that y of j omega, right? Y of j omega can be written as is equal to how much it is, so 1 over absolute of a, so that's 1 over uh, how much a is, so it's 1 by 2, right? And the frequency is scaled by omega by a, so that means this is x of j omega, so it will be equal to I hope you understand, or should I go stepwise? Right, okay, I write it stepwise. So this is how the relationship is. So 1 by 1 by, it will come into 1 by 1 by 2, and x of j omega by a. So this is x of j omega, right? So that means we replace omega by a, right? So omega by a is how much? A is basically a equals to 1 by 2, right? This is the scaling factor. Okay, so when a equals to 1 by 2, that means we replace omega by a, so that means we have 2 in divided by omega. So this again omega, and we have this thing omega by a, so omega by a is 1 by 2. Is it something like this, right? And multiply by sine of, so sine of uh, omega by a, right? Again omega, so by a is 1 by 2, right? So on simplification, because this is double division, right? So you understand, we can straight away write it as 2 omega, right? Because double division is basically multiplication, so this will be 2. And again, this is like uh, one, how much it is? Okay, so I think, can we straight away cancel this one, right? So we get y of j omega as 2 by omega into sine of 2 omega. Okay, so I think it's clear to you, right? So here is the graph, right, for the problem we have just considered. So this is our x of t. It has value of 1 from -1 up to 1, and it has in the scale version y of t, because y of t equals to x of t by 2. So this is the scale version. So scale version is basically stretched one, right? So this is the Fourier for the original signal, and this is for the uh, stretched signal, right? So you understand why we have higher peak here, because if you take the, because at omega equals to 0, we have the 0 by 0 format. At that time, at that point, you take the L'Hopital rule, and when you take the L'Hopital rule, because sine is now 2, previously here it is sine omega, right? But here it is sine 2 omega. So when you scale it, when you take the L'Hopital rule, based on that, you get at 0, you will get the double value of what you have here. So hope you understand this, right? The next property we are going to consider is the differentiation in time, right? So for example, we have a signal x of t, right? So the inverse Fourier transform, right, x of t equals to, using the inverse Fourier transform, 1 by 2 pi e power minus infinity, integration e power minus infinity up to infinity, and x of j omega e power j omega t, right? So to derive the relationship for this property, let's integrate both sides with respect to time. So x of t, right? So we are taking derivative with respect to time. So on the left side, we get this thing. And from the right side, you understand x of j omega is constant because we are differentiating with respect to time. So e power j omega t, if I differentiate with respect to time, so I'll get same multiplied by j omega, right? So I get j omega times this. So that means differentiation in time domain results into multiplication by j omega, right? The results into multiplication by a factor of j omega to the x of j omega. X of j omega is the Fourier transform of x of t, right? So hope you understand. So let's to elaborate this further, let's consider an example. For example, we have a signal such as shown here. So right, so we have to find the Fourier transform of it. So that's quite straightforward. Instead of taking the Fourier transform of this derivative, we can straight away take Fourier transform of this signal and multiply it by a factor of e power uh, by a factor of j omega, right? Because this is the property. So you understand Fourier transform of e power minus at is simply, right? So Fourier transform of e power minus at u of t is simply 1 over 1 plus j omega. This we have already done, and if you are confused, so you can do it again by just writing it something like we have, right? From minus infinity up to infinity e power minus a t, right? And multiply by e power minus j omega t and dt. And you understand, because here we have u of t multiplied, so we'll just integrate it from from 0 up to infinity, so you'll get this, right? And by the exploiting the differentiation in time property, so if I put here derivative d upon dt of this, then simply you multiply j omega with it, right? So let's verify this by using uh, first differentiating it with respect to time, and then finding Fourier transform of the resulting signal. So we have two functions, right? They are multiplied, so you know the product rule for differentiation. So you say, okay, first function into derivative of the second function plus second function into derivative of the first function. So first function is your e power, for example, not for example exactly, your first function is this one into derivative of the second. So what is the derivative of the second? So if you recall, derivative of the second is basically impulse, right? Because step function, if differentiated with respect to time, will give you the uh, impulse function, right? Then we say, okay, second function, now the derivative of the first function. So what is the derivative of this one? So this is basically e power minus at, and what is the again derivative of minus at? So we'll have minus a here, right? And you write u of t as it is. Okay, so by now I think you understand, because Fourier is also holds the scaling property, so you can straight away exploit this. So you know what is the Fourier transform of this one. So Fourier transform of this is basically what? So Fourier transform of this is basically minus a, right? Fourier transform of this one is just let me, right? The Fourier transform of this one we have just done is this, and this is equal to e power, this is equal to a plus j omega. Now because we have scaled it by a factor of minus a, so I just write here minus a. What is the Fourier transform of this one? Right, so if you look at this one, this is an impulse. So if you integrate it, right, so that means this impulse has value of what, right? If you recall, uh, because this exists at t equals to 0, it is non-zero at t equals to 0 when t is 0, so this whole becomes 1, right? And this is your impulse. So what is the derivative of impulse? Is it 1? Not derivative, the Fourier transform of impulse, right? So because this whole is equal to impulse, the product of impulse with this one is basically impulse, right? This is the shifting property we have already done. So we can also say that this is basically equal to uh, e power 0 times the impulse of t. So e power 0 is basically 1, so we can say this is basically this equal to impulse of t, right? So what is the Fourier transform of impulse? So this is basically 1. Now this, what we get here is we can just say, okay, this one, right? So we have 1 minus a over a plus j omega, right? So that means if I take the LCM is a plus j omega, and this will be a plus j omega minus a, right? So because its denominator is 1, so the LCM of this is this one. So when I divide this by 1, so I get the same. So 1 multiplied by a plus j omega, and then we come to here. So I hope you understand how the LCM works, right? So if that means minus a cancels with minus a, so what I get j omega over a plus j omega. So you understand that's a lengthier procedure to find the Fourier. That one is quite straightforward because we know what is the Fourier transform of e power minus at. This is 1 over a plus j omega, right? Yes, we multiply by u of t, right? That's causal. So for causal exponentially decaying signal, we have this Fourier transform. So if I take derivative, it's straight away derivative at time domain equals to multiplication by j omega. So I have the Fourier transform of e power minus at u of t 1 over a plus j omega, and for the derivative I say okay j omega over this. So that's quite straightforward method, right? So you can use any, but you understand that when you use the properties, you exploit the properties, then you can do it very quickly and very easily. So we are talking about the properties of Fourier series. This property is differentiation property in frequency. The previous one was differentiation in time. Now we are having differentiation in frequency. So for example, x of, yes, you understand x of j omega equals to e, right? This is the analysis equation. Okay, so if I differentiate the analysis equation with respect to y, not with respect to y, with respect to omega, right? Because we are in the frequency domain. So if I differentiate with respect to omega, then if again x of t will be constant because we are differentiating with respect to omega. So this one, if I differentiate, right, so e power minus j omega t, by differentiation I get the same e power minus j omega t, and then multiplying the this one again derivative minus j omega t. So if I differentiate with respect to omega, I get minus j t. So I get minus jt x of t e power minus j omega t dt, right? So uh, basically that's the time domain, right? So that means in the frequency domain, differentiation, right? Differentiation in frequency, because you understand we are taking the Fourier transform of this, right? That's your signal, original signal, this one, and you understand multiplication by e power minus j omega t, uh, and integrating from minus infinity. That means this is your signal and you're taking its derivative. So that means this is your time domain signal. So you can say that in time domain minus jt x of t, in frequency domain this. So that means differentiation in frequency domain is actually equal to multiplying it by minus jt. Okay, so again we have a problem here. We have x of t equals to t e power minus at u of t, and we need to find the Fourier transform of this. So I hope you can straight away do it, right? Because what is the Fourier transform of x of t? So the Fourier transform of x of t e power minus at minus at u of t is 1 over. So you can exploit the property and easily find the answer for this one, right? If you cannot find, then I'll help you in the live session. The next property we are going to consider is the convolution property. You understand, in time domain we have done the convolution. So in time domain, if the two signals are convolved, like we have y of t equals to h of t convolved with x of t. So if I take the Fourier transform of this equation, then y of t has Fourier transform y of j omega, and h of t has h of j omega, and x of t has x of j omega. And you see that convolution in time domain basically results multiplication in the frequency domain. So multiplication in time domain basically convolution in time domain results into multiplication in frequency domain. Similarly, if two signals are convolved in frequency domain, then in time domain they'll be multiplied. So that means we can go to the frequency domain to get our job easier when we have convolution in time domain. Similarly, if we have a convolution in frequency domain, we should come to the time domain, multiply the two signals, get this product of the two, and then using inverse Fourier transform we go there. So it will make our job a lot easier, right? So let's consider an example. So this example we have already considered, right? So for example, we have a one of the examples we have considered. So let's consider just a single example, and we say, okay, we have a signal x of t which is equal to 1 by pi t into sine of pi t, and we have x of t equals to this, and we and impulse of t equals to this one, and what we have to find the output signal, right? So the two signals which are this one the response and this one the input signal, they are quite difficult, right? So in time domain, because the output is equal to the convolution of the two, so convolution for this signal is very difficult. So let's exploit the Fourier transform and find the frequency domain signal for x of t and h of t, multiply them, and then use the inverse Fourier transform to find y of t, right? So because we have already done this signal, right, and this is basically an impulse in frequency domain, right? This is sync function in time domain, so this is basically impulse in not impulse pulse in the frequency domain. So if I plot the signal, it will be something like I'm plotting its frequency domain, right? So here the equation is given, so the Fourier transform of this will be equal to 1 for omega is absolute of omega is less than or equal to pi, and 0 otherwise. Similarly, for the impulse response signal, we have its Fourier transform equal to 1 when absolute of omega is less than or equal to 2 pi, right? So you know the y of t, right, is basically equal to x of t convolved with h of t, right? So if I take the Fourier of these, then I can say that basically these are equal to Fourier transform. And what is the Fourier transform of y? This is y of j omega, and y of j omega equals to x of j omega, whatever you write first. Okay, let me write x of j omega times h of j omega, right? So that means it is just the multiplication. So if I plot the two signals, okay, I have x, for example, this is frequency, and x of t, if you look at this one for omega is less than or equal to pi. So that means this signal exists from here up to here, and this is minus pi, right, and this is plus pi, and beyond this it is 0. Similarly, if I plot the response signal, so the response signal is uh, 1, right? For omega, absolute omega is less than or equal to 2 pi, so that means let me plot with a different color. So it will be something, this is like 2 pi, so plus minus 2 pi, so that is basically equal to this. So this is your minus 2 pi, right? And this is the 2 pi, and this is omega, and this is your x of t, sorry, x of j omega, because we are in frequency domain, so x of j omega, and this is h of j omega, right? So in frequency domain they are multiplied. So if I take the product of the two, you understand that's quite straightforward. You are familiar with the multiplication of the variable, so you can see that x of j omega is variable, h of j omega is variable. So when I multiply them, so from minus 2 pi towards the left, this signal is 0, this is also 0, right? So the product will be 0. Again, this is the point of minus pi, right? And this point of plus pi. So again, from minus pi up to 2 pi, although this signal is non-zero, but this signal is 0. Okay, so the product will result into 0. So that means we have the non-zero value y of j omega, right? Y of j omega equals to 1, and when it will be 1, when omega absolute is less than or equal to pi, right? So I hope this gives you ideas. 0 otherwise, right? That means for all other values it will be 0. Okay, so you understand. Similarly for this part, so from minus pi up to pi this is 1, and from minus pi up to pi this signal is 1, so the product will be 1. For other, from pi towards infinity, this signal is 0, so the product will result into 0. Similarly this one. So I hope this type of signals I have explained many times, so I hope you understand. So that's your y of j omega, but actually your target is not y of j omega, your target is y of t. So how to find y of t? That's quite straightforward. Take the inverse Fourier transform of y of j omega to get y of t. Now if you look at this one, y of j omega, this same is as x of j omega, right? So that means if I take the inverse of this one, it will be exactly what the xt is. So that means y of t equals to what? This is equal to 1 over pi t, right, into sine of pi t, or you can also say whatever is the x of t, that is y of t. So you see that it has made your job quite easy. So with this we end the lecture for today, and we'll start the new lecture with this numerical problem. This you have already done when we were doing the convolution sum, right? So go through the lecture, and if you have any confusion or you want to add something, so we can discuss. Okay, Allah Hafiz.